But we're going to start differential equations today. If you hear the word differential show up in math, what other math word does it relate to? Derivatives, right? Differentiation. And what have we been studying in 4.8? And an antiderivative just undoes a derivative, right? So if I have an equation that has a derivative in it and I want to solve it for the original equation, we need a way to undo the derivative, which there's great news with that because one more time, what did we do yesterday? Antiderivatives. And what does an antiderivative do you think, to a derivative? It undoes it, right? Like it's just they undo each other. So it means that we now have a tool, and we're going to come back to these once we get a little bit more sophisticated with our antiderivative stuff. But to start us in today, we are in the second part of 4.8. And today our focus is going to be solving the basics. I'm not going to put that. We are solving what we'll love or call differential equations. And because this shows up so frequently, you could call it ODE. And that's a great piece. Like I just didn't even think about it. Because we're not going to go crazy into them, you will hear me regularly refer to this as diff EQ. Differential equations, diff EQ. That's how it was commonly referred to where I'm from. ODE and PDE, you'll get to eventually. But let's jump in. Let's first define this. And it's kind of redundant, but we need to make sure that we're all comfortable with what it is that we're actually solving. I don't know why, but when I write all caps, sometimes my spelling comes out funny. Differential equations. And we'll do the same thing, diff EQ. Okay, differential equations. Now, if I said that I had a quadratic equation, what does that tell you guaranteed is going to be in there? So we'll turn and talk. If I say, hey guys, we're going to graph a quadratic equation, we can all agree that it's going to have something that we know it has. Turn to your neighbor, what does a quadratic have? Or what does a cubic have that makes it a cubic? A quadratic has a what? A power of 2. X squared shows up, right? A cubic has a x cubed. A log function has a base, but could you agree that it's a log? Like, and you're right, logs do have bases, but a logarithm in it, right? What do you think a differential equation will have in it? A differential, and that's like our fancy way to think about what? It's a derivative. We have equations that have derivatives in them. That's it. So when we're defining these, that's all we need. We're just going to say that a differential equation, or diff EQ, is simply an equation, and remember EQN is my shorthand, with a derivative in it. That's it. Now, we could get much more fancy with this if we needed to in it. We don't right now. And most of you, or some of you, depending on what you ultimately study at university, you probably will go more into this. What I love about differential equations and what I think is just mesmerizing about it, and I probably made this comment yesterday, you can solve problems that analytically cannot be solved just by being able to do these. And there's some really fancy techniques. Mrs. Holloway, I don't know, some of you guys had her. Do you know what Mrs. Holloway studied in college? Anybody remember? I'm sure she told you. It was not math. So science, yeah, I would agree. Mrs. Holloway by trade or by education is a geophysicist. So her job that she wanted to do, she's not super into geology, but she wanted to be the person that worked for the big oil companies to go in and say like, oh yeah, this is where we need to drill. Because there's a lot of money if you can tell a $1 trillion company where they need to drill to make trillions of more dollars, right? Ultimately, she did not wind up committing to a career with that. Like she taught science for a few years, and she may again at some point, maybe, I have no idea. But the important part of that is when she and I met, it was in Wyoming. I'm not telling you my whole life story, just for the record. Sounds like we're going that way, but it's not where we're going. She was doing a doctorate program in geophysics, and ultimately she decided that it was kind of boring, which I agree because rocks bore me personally. But her advisor, the person that she was working with, her doctorate person that was going to help her become a PhD, was doing some geophysics stuff, and he was doing something with rocks and density to figure out where there's oil. And his big claim to fame was he found a new method for solving differential equations because there's so many variables at work that you can't make good predictions, but you can make generalized predictions from this without being able to actually find the equation, which is awesome. We can solve stuff without knowing what it is truly that we're solving, which sounds crazy, but it's a really, really powerful tool. And we're going to start to see the beginnings of that tool. So right after these, let's just chat about a few little things here. We'll just make some asterisks. We want, or we are trying to find, we are after, if you will, like what we're chasing. We are after a function. And we're going to call these functions of the form y equals cap f of x, for which, and I'm going to let you guys catch up because we get kind of mathy for a minute. We are really and truly not looking for just an x value anymore. We're looking for a function that makes the following work. So we're looking for a function for which, and I'm going to put this here because it stands out, we need it to be true that dy dx, which, what's y defined as? Cap f. So this is the same as saying cap f of x, but there's one more little mark I need. Prime, love it. We need this, and what is the derivative of cap f? Or if I reword this, what is the derivative of the antiderivative of f? It's just f, right? We are looking for the function that makes this true. What function did we start with is what we're really, truly looking for. Now, more specifically, if this is kind of gross, and yeah, kind of is, too big, a little follow-up for this is essentially we want a function who has this as the derivative. That's it. Do I need to write that part down? Okay. We want a function f. I'm going to call this cap f, whose derivative is lowercase f of x. That's what we're after. So we're trying to figure out the connection between how something changes and what equation did we use to figure out how it was changing. That's the connection we're making. Okay. Now, I promise that this sounds a lot worse than it's about to be. Now, what we care about most in here is what's called a general solution. Yesterday, and when I have that plus c, how many choices do we have for that c value? Infinitely many. And we said that if you were to graph an antiderivative, you're really doing more than one graph. You're graphing a whole something of functions is the language we used. One more time. An array of functions. I kind of like that word. It works for it, but I used an F word. That's not factor. A family of functions. We're looking for all the functions that look kind of like this. So our goal in here is we're going to be looking for what is called the general solution, and we're going to sneak into vocab. The general solution, and remember SOL apostrophe N is my shorthand for solution, is the family of antiderivatives whose derivative is little f of x. So we're looking for that whole, exactly what we were after yesterday, the something plus c. So we get a whole family of functions that if you were to differentiate it, we get back to some particular function. Now, that is a very interesting word, unintentional that we used it. We have general solutions, the whole family. Okay. I lied. I'm going to hold off on questions until we try one, and then we'll come back together and see like where do all the questions really live. So we have general solutions, which is a bunch of stuff, whole families. Contrasted with that, we're also going to be asked to find some more specific or particular solutions. And there's a lot of vocab just at the front, and then the rest of it's just going to be all problems. Not weird. The particular solution. Now, we're going to get more specific with this, but if I want a particular solution, all it means is if I give you infinitely many of these, this whole family, where it could be any of these, however many graphs, all of them, I'm looking for the one that fits some specific data that we're given to begin with. So we're not going to go crazy with this definition, but we're going to say the particular solution can be found, and we will find it, can be found if we know a boundary condition. And that by itself doesn't really clear a ton up for me personally. And I'm going to give a synonym or a synonym here in just a second. We can find which of these infinitely many antiderivatives needed to work if we know some boundary condition. Now that is an odd choice of language. It's what your book uses. Is the only reason I'm doing it here. What we mean by this, and this is a much more common way, is we need to know some initial condition. Now, for this, there is a really easy place, even before we solve one, to see in like easy way to see where, oh my gosh, I can't speak right now, I'm sorry. One really good example of where differential equations matter is there's a lot of stuff in our world that if you change one little part of it, it changes the whole system. So for example, weather predictions are really good for a month from now, right? No, weather predictions are garbage if you try to predict a month out. Why? What's one little thing that could change that would change the whole global weather pattern? If temperatures were 1 degree Celsius warmer than we thought they were, do you think that 1 extra degree or that 1 degree of extra energy would change that local area? Like if I have a storm and I say, it's going to be this big because I think the water is going to be 20 degrees Celsius, but then the water is actually 22 degrees Celsius. Do you think that storm is going to be stronger or weaker? Probably stronger, right? We have more energy in it. Now, if my whole weather prediction was based off of this storm happening at 20 degrees, if I change 2 degrees, it's going to change that original storm, right? Will that new change in that storm impact weather patterns over here? Like right next to it. And now they change differently than I thought. And when they change, will it change the other weather patterns? So we can see that just one small change, it's like the butterfly effect, right? One little tiny change somewhere impacts the whole system. If we know exactly where it started, well, then maybe we could figure it out. Now, weather's a bigger differential equation than anything. And if you want a little sidestep, I can pause it and give you my philosophy take on this also. But we can also just do some equations. Let's do some equations. We'll come back to philosophy. Okay. You guys ready to get mathy? Sweet. Let's find one. Now, our first example, we are going to find a particular solution. So here we go. Example. Let's find, and I want to see how I word it. Find, and I lied, we're going to find both the general and in particular solutions. And we're going to do our first one together, and then we'll figure out where are we lost. It sounds like I'm expecting you to be. That's not necessarily true. This stuff makes it feel hard in my head. I think they're going to be easier than you anticipate. All right. Should we jump right in, or you want the word before we go? We've had a lot of vocab. Okay. I like that you answered, Rafa. I appreciate it. Cool. So here we go. I want to solve the following. On example A, here's what we're given. I'm told that for some function, dy dx is equal to 5x squared plus 2. Okay. Now, more so, I know that the following, and I'm going to make a state which says where, I'm told that whatever these are representing, the 0.35 shows up on the graph. Now, I'm going to make sure that we're all on the same page. I've given us a what right here? This is a derivative. Okay. Now, if you don't have to put this, like, it's okay, right? You don't have to write everything that I do. Where 3,5 is on the solution curve is how I'm going to word that. Now, here's the big part that we need to be able to connect. When I solve this differential equation, my answer is going to be a function. Now, it's going to be an easy function because all I'm looking for is the function that has that as a derivative. I just need to find y equals. Undo this derivative, so that instead of dy dx equals, we just get to a y equals. That's the whole goal. When we say this part, 3,5 is on the solution curve, and I'm not going to go crazy with this, and I wouldn't have you draw this, But if we think of a whole family of antiderivatives, here's a bunch of them, right? Does one of these have, and this, I don't think it's a parabola, but is 3, 5 on one of these specific graphs? That's the particular solution. When we say it's on the solution curve, we'll say the original, and we could say OG if you'd rather, the non-differentiated, the original y, not y prime. We are looking for, we're told that we know a point that's on y, and we're given how y changes. Now we need to find that original function. Okay. So from here, everything in red is just like the talking. Let's make sure we understand the pieces. And now we actually get to do it. So I'm stuck. Right now I have dy dx, and I'm going to annotate like crazy. How do I go from dy dx if I wanted to get right to my next line saying y equals? What undoes a derivative? So check this out. Now, we don't have a nice way to write it for ourselves right now, but algebra is still at work. If I take the antiderivative of the left, I must also take the antiderivative of the right. So we're going to say anti-differentiate. I'm going to use anti-ddx, both sides. That's how we're going to start with this. Now, it's nice because we start with just dy dx, nothing crazy. I have anti-differentiated the left. I'm going to give you a moment. I want you to anti-differentiate the right side. So we're just checking, can you still do the antiderivatives? I'll give us about 60 seconds walking around to get my steps and to make myself available for questions. Check with anybody and see if they need help around you, because I agree with you. Maybe. I want to look at one thing. Love it. What do you think? Is it a C? Yeah. Love it. Check with your neighbors. What do you think? So good. Now I'm going to pull something up in your text just so we can use it here. And we're in 4.8. Because if you don't have them locked in right now, like it's fair, because we only did it like 2 days ago. But I do want to look just to make sure we have it. I want this one. This is the one that I care the most about because this is the one that's going to be most common for now. That's that first situation. That's that one, right? So check it out. What happens with this exponent? Instead of moving to the front and subtracting 1, we add 1 and then divide by it. So instead of x squared, add 1 to this, it becomes x cubed. So it's 5x cubed. And then instead of, love it. Love it, love it, love it. You're missing one thing. Okay. Little piece by piece. This one's not bad. How do you take the antiderivative of an x squared? So let me try this again. Leanne, how do you take a derivative of an x squared thing? Good. So that becomes 5x cubed. What else do I need to do? One more little piece. Love it. So 5x, we add 1, and then we divide by that new exponent. Cool. Plus, Bea, what's the antiderivative of 2? Love it. Now, we could, and if you are struggling with these, is that the same thing? 2x to the 0? So we're just going to use that same rule, right? Add 1, it becomes 2x to the 1, divided by 1. It's still 2x. It's the same rule at play. Anything else? Oh my, important. Right now, do we have a specific one function in particular, or do we have a whole family of functions? How do you know that? Why a y family? Because it's plus c, and literally infinitely many c values that we could pick. So right now, we have a function or a family of functions that have this as a derivative. The whole family of functions that have that as a derivative. What did we just find? We just found the general solution right now. So I'm just going to note that this, and I hate how that y equals looks, so I'm going to fix it because it's annoying me. But we know then that y equals this right here is our general solution. And I don't think it's a stretch here. Anybody look at this and say, what on earth did he just write? Everybody know what I'm shorthanding here? Verify that. It's the general solution, right? Okay, so we have it. Now, we get to go a step further. This is fine and dandy. I know that it's one of these infinitely many functions, but I want one function in particular. And what I know about that is there's a 3, 5. What's the only thing about this that's going to change that would give me one specific function? I need the value of c, right? So I'm going to make that note here, just like we did before. We'll just go this way, and we'll say between these steps, to find the part solve, or the particular solution, we need to find c. If we can find the value of c, we have that exact function that had that derivative and this initial condition, or this boundary. So how on earth can we find c in this problem? If only I knew a point that has to be on this graph. Oh my goodness. Somebody quietly whispered confidently 3, 5. That's the point that we know. What am I going to plug in 3 and 5 for? Yeah, we're going to use that point, and I'm just going to be using x equals 3 and y equals 5. So now I'm going to rewrite this, but I'm going to leave a bunch of blank spots so they stand out. And let's just see. I'm going to plug 5 in for y. So here it is. 5 is for y. And let's see. I'm going to leave this blank. It's going to look silly for a second, because I'm just going to put everything, I guess, so I don't have to change colors a bunch. And what am I going to plug in for x again? So here we are, and here we are. Can I solve that equation for c? Do that for me, and report back what you get. So I'm going to show you something, because I think you're faster. What's 3 cubed over 3? So careful.
Oh, wait, 3 cubed is 27.
So, and you're thinking more about it than I would. You're doing 27 divided by 3. Do you agree that it's just going to be 3 squared? What's 3 squared?
9.
Times 5.
9.
Plus 6.
50.
You can do this faster probably in your head than you can with a calculator. It's okay if you want to use your calculator. I just want you to make sure that you know that. What'd you get for C? I have one claim at negative 16. Can I get a second or a disagreement? So let's do some looking here. Negative 46 is the other one. 5 is equal to, what does this shake out to? So let's just do a little bit of scratch work. 5 is equal to 45 plus 6 plus C. 51, I'll subtract from both sides, negative 46. Sean, where was your mistake, out of curiosity? Did you just do it in your head? Okay, so it's going to be a little harder to find it, right? I don't think that, like, I know you can do this. I don't know where your mistake happened. I'd verify on yours as well. So now what? We have C. Can I write the very specific function that we started with then? We're one step away. How do I now get my particular solution? I'm just going to plug in C, right? So here we go, and I'm going to make this one stand out. Let's see, our particular solution is going to be y is equal to 5x cubed over 3. And I'm just taking this one, and all I'm doing is adding the C value we needed, plus 2x minus 46. And look at that, we are done. Now, for this, I'm going to do the same thing. What solution did we just find? Not the partial. The particular. One solution in particular is what I always think of in my head. The particular solution. Now, we haven't gone into like the really cool application stuff yet. We're just easing our way in. First gut feelings. Easier than you thought, harder than you thought, or about what you were expecting? I don't know what yes means, just for the record. Easier? Good. Can they get hard? Probably. Do you think ours are going to get crazy, crazy hard? We'll see. I don't know. We'll be the judge of that. Now, the cool thing is that we have some language that's pretty common in how we talk about how hard these things get. So right now, we had, what was the highest derivative that we had in this previous problem? Is this a first, a second, a third, a fourth? It's a first derivative. So check it out. We can start specifying these, and we're just going to do some more examples together, but we're going to sneak in a little bit more language as we go. So example, I'm just going to call this one, and name it, I guess, our goal is to solve each of the following. So I'm just going to say each. And if I want to say I have a differential equation that is only in first derivatives, we're simply going to say it's a first order differential equation. And I'm going to use diffie-q for this. And again, you don't have to write everything, but if you want to have this nice and defined, first derivative. That's it. One single derivative. If it happened to be a second order, how many times do you think we would need to take the antiderivative? Twice, right? Like, and we can get a third order, a fourth order, and all of that stuff. So these are first order, and I'm not going to write it here, but these are ordinary differential equations is all that we're doing. So let's check it out. And by let's check it out, I mean I want you guys to check it out. So for our first one, here's what we know. We are told dy dx, this differential, is the following. It's negative sine of x plus 1. But I'm given more. I know that on the original graph, I will find the point pi comma 1 as initial condition. Okay. If you're watching this on the road, I want you to pause it now and go ahead and try to do this. For everybody in here, I want you to work through this independently with your neighbors. I'm going to give you guys like a 90-second head start, and then I'll start working it. But I want to remind you again, I'm walking around so that you can ask questions. I want to see what you come up with and how this goes. We'll meet back up. Cool. Once we're here, we have the general. How do I go from my general to my particular? And I'm going to be much less wordy. What do I plug in? X equals pi. And you can just write the ordered pair, and really you don't need this, just my annotation. And solve for what? Good. Now, I can show the scratch work if we need, and it's a good trig review here. Let's just see where this shakes out. I'm not going to change color this time because it takes me too much time. I know that it's 1 when I take the cosine of pi plus c. Okay, real quickly, on the count of 3, with all in agreement that this is 0 radians in your perspective. Is that true? This is 0 radians in your perspective. Count of 3, you're going to point to pi. 1, 2, 3. Pi it up. Cool. It's all the way over here. Anybody not comfortable with that question? So we should maybe do a unit circle day at some point. Just throwing it out there. It's not a threat. If you don't get something, I want you to get it. I know it might seem like a threat, but really it's for you. Okay. What do we get for cosine of pi? What is my, sorry, over here. No, backward again. What's the x value here? Am I in the wrong side again? I'm not at pi right now? So that's 0. Okay, you're right. All right, sorry. I had to. So what's this? Sorry, what's cosine here at pi? There we go. Thanks. My bad. So let's see. Just doing a little bit of substitution. 1 plus -1 plus pi plus c. What do we get for c? Add a 1 to both sides. We get a 2. Then I have to subtract the pi. C is 2 minus pi, I think. Did you guys get the same thing? Fantastic. So what do I do? Interesting that I have a very different answer on my sheet. I have a typo on mine. I trust this, though. So what? Plug it in, right? There's a commercial that has that song in it, but I don't remember what it advertises. So why? Yeah, what is it advertising? Plug it in, plug it in. You guys know that one? What are they selling me? Probably an air freshener. That would make sense. I don't know. Glade. It's Glade. Cosine of x plus what? Awesome. And we're done. What did we just find? What is this one? That is our particular solution for this data. All right. Feels good still? Feels bad? Do we want another first order, or are you guys ready to bump it up a little bit? All right, let's bump it up. But first, I have a question for you. Nope, that was yesterday. I'm just hiding this. Circumspectly. What does this mean? Your math minds are going to betray you. What's up? Sometimes what? Observant. Interesting, because you're seeing spectacle. What's circum? What does that make you think of? Circle stuff. So in my mind, I think like circling back around or something like that. Cutting may be reasonable. It's an adverb, which means it does what? It describes how you do something. So a verb, right? So it describes a verb. Okay, check this out. Cautiously. Nothing to do with a circle. Did you know that, Aisha? I've never seen this word before. Never. Done in a cautious way. Warily. Cool. Holloway willingly but circumspectly shares his personal opinions. Very cautiously, right? Like, I don't want you to know anything about me. Cool. All right. But now that's not really true, right? Like, you guys know a little bit about me, but I like the mystique. All right. What's up? Maybe. Why'd you think that? That's true. Men do plunder. All right. Let's do another one. Let's bump it up, though. And I was trying to clear my screen. Questions about the last first order derivative before we move on. Sweet. So everything's gone. It's dead. Let's do second order. I just ran out of space. So example. We're going to solve, and this time we will do a couple of them. We'll say solve each second order. And we'll do the first one together. Differential equation. And just so you guys know kind of where I'm heading with it, we're nearly done with the chapter. Like, and that's not supposed to be a threat. When we do this, we're going to go through like the pure mathy version of this, and then maybe today, but definitely tomorrow, maybe just more tomorrow, we will be doing like actual real world application stuff so we can see where this stuff works rather than just doing the pure mathy versions. But without any further ado, let's knock one out. So here we go. On A, I want us to solve the following differential equation. We have d squared y dx squared, which is a really awful mouthful to say, but what am I really giving you? Now, we're going to logic out a little bit just before I write it. How many points did you need to find the constant from a first order? You just needed 1 point, right? Now, when we do our first antiderivative, we're going to get a c value with it. And then when we do the second one, we're going to get a different c value. And I know that they're going to combine to be a single c value in the end. But if I have two different values that I need to solve for, how many initial conditions do you think I need? Probably two, right? Because we're going to have to plug stuff in multiple times. So we'll keep that in mind. We have our differential equation, and we're told that a second derivative of some function is 2x plus 1. And what I know about the function that gives me this second derivative is that it contains the points 0, 2 and the point 6, 98. Now, this could be a variety of things, right? At time 0, my position was 2. At time 6, my position was 98. And I can already see that, oh, yeah, there's physics waiting to be done. Whether this is a physics problem or not, I don't know. There's no context. How do we start? Get to the first derivative. If you add the get, I didn't know if I heard it. How do you go from a second derivative to a first derivative? Yeah, let's take the antiderivative. So I'll do the left side. And here we have a notation choice to make. We have been using the very formal version of this. Is there another way that we could write derivative? So yeah, if you would rather, I'm just going to say here's the antiderivative. If you would rather, I have no issue with saying y prime. I'm good with that. Equals, and help me out here. 2x antiderivative. 2x squared divided by 2 x squared, okay? Plus antiderivative of this is x. And then because I want to be able to keep track of my constants, I know they're going to combine in the end, but I know that there's going to be a constant here and a constant on the next one. How do I differentiate, no pun intended, between this constant c and the next constant c? Let's use c1 and c2. Let's just keep stuff straight for now. I'm going to call this c1. Now, currently, do we have enough to write our general solution? Now, be very careful because I see like somebody's going to think yes, and I totally get it. But the general solution is going to be the function y that this second derivative came from. What function do we have on the board right now? Y prime. So we're not quite there, but we're almost there. There's one more step right off the bat that we should knock out. Take the antiderivative again. Let's do it. So we'll go one more step. And I'm just using anti as a shorthand for annotation. And we would get down to y at this point. And y is equal to x cubed over 3 plus, so we'll get there. Everybody okay with x squared over 2 rather than me waiting for it? And Sean asked a great question. What is the antiderivative of c1? What's the antiderivative of, well, so people are saying c2 and I get your like intuition there, but be very careful. What's the derivative of 2? That's a constant. Sorry, what's the antiderivative of 2? You guys were right. 2x. What's the antiderivative of 5? A different constant. So what's the antiderivative of c1? So I'm going to call it c1 times x, but I agree. And then notice, there's our antiderivative, and that's the weirdest part. What else do we have to tack on here? There's another constant, right? Because we did the antiderivative again. What should I name this one? c2. Right now, I have the whole family for infinitely many c's. What is this solution? This is my general solution right now. This is the family of functions that this works for. Now, we want to get down to the particular solution. Is this a together exercise, or is this one that I let you play around with? We'll do the first one together. Like, we'll just see what shakes out. So let's dig in. If I have no idea what to do because there's so many x's and so many y's, what did we have given to us from the initial set, the initial conditions? We have some x's and y's, don't we? Huh. So let's check these out. Which one do you want to use first? 0, 2. Let's use this one first. And I'm going to switch color. We'll do this one in green. So if I do this, I get 2 is equal to 0 over 3 plus 0 over 2 plus c1 times 0 plus c2. And I'm going to put a star next to this so I don't lose it. I think it's already clear. What is c2? c2 is 2. Has to be, right? Okay, so that's all fine and dandy. We want to find the next value. Now, I'm going to make a mistake. Not really a truly mistake, but I want to do something wonky, and I want to see if we can pick out what you would have done differently before you just copy it. I now will probably use this point. Seems natural, I hope. Everybody agreed we're just going to plug this one in now? 98, fine with that. What am I plugging it in? It's just this still. So help me out here. I'm going to keep that 6 cubed for now. Over 3. Plus 6 squared. And you can clean these up if we want. I'm just doing a little tiny step. Here's the biggest part. What do I put in for C1? Do I know it? So it's still C1 times what? 6 and one more piece. Plus 2. The most common mistake that I'm going to see you guys make, maybe not now that we're really addressing it, is people forget that we've already found one of them. We have to use the value that we found. Otherwise, we're going to have 2 unknowns still, and we can't do it. But with all of this, I'll give you a moment, whether it's with your calculator or by hand. I want you to find C1. And I'm just going to put ... some algebra happens, and we're going to get C1. I'm going to give you guys a minute, play around. I don't care if it's calculator or mental math. 216 is 6 cubed if you're just dying to know. Cool. We'll meet back up shortly. Ladies, if you're watching this on the road, please pause it now, and when you resume, we'll continue working and finish your problem. I now have C1 is 1. I know that C2 is 2. Those were the only things I needed to get which solution. Here's my particular solution then. Let's write it out. Y, then, my original function that we must have started with, was x cubed over 3 plus x squared over 2 plus how many x? One of them. And it's weird that we get the second one first and we have to like be very careful in why we label stuff. C1x, right? It's 1x if you want me to write it. Like you can. People often will get those goofed up. The subscripts help. Plus, finally, what's the last little constant? 2. And look at that. We have a particular solution right here, and we're done. Now, we will get into the application stuff, but I just want to stress here real quick. It's like I told you that the original function, and let's just play some physics thought real quick. In physics, when we think about position and all those good things, what's the second derivative? Acceleration. So the problem that we're working right now says, so here's a function for acceleration at time x. That's what it is. But now I know that originally at time 0 my position was 2, and at time 6 my position was 98. If I find that this antiderivative, we were at acceleration, what does this give me? This is now my velocity function. Cool. If I know the velocity function and I anti-differentiate it, I get down to what? Position. So we are finding the position function with these initial positions that we're told that gives me this acceleration. Like we just made it the word problem. Now setting it up and recognizing that it's a second order or first order, whatever, as long as we know position to velocity to acceleration, you're going to be okay with the physics stuff. Quick follow-up for fun. What do you call the rate of change of acceleration? Say it again. Not torque. Starts with a J. Jerk. It's jerk. And it makes sense if you've ever ridden in a car with somebody learning to drive a manual and their acceleration changes constantly because they can't figure out the clutch. It's a jerky ride. The next three are more fun. Jounce is the alternative, just so you know. Jerk or jounce. I like jerk. What's the next three? Snap, crackle, and pop. And I can't even begin to tell you what the realistic representation of what it feels to have a snappy ride. I have no idea. Really jerky, jerk changing speed constantly. Okay, don't worry. Before you pack up, I got something for you. Your homework tonight is much less formal. You are doing one problem. You get one problem in your notes for homework tonight, and I'm going to give it to you right now. I'm going to tell you that d squared y dx squared, which I would write y double prime, is equal to 12x squared. And I'm going to write this a little bit differently. If I write IC, any guess on what it is I'm referring to? The initial conditions. Awesome. So I'm told that whatever this is representing, the original function had the points 0, 1 and the point 38. Cool. I want you to bring me the function tomorrow that has this second derivative, but f of x has these points, or y. Sweet. One problem. Study hall's in here after school if you'd like to attend. I'll see you cool cats and kittens later.